Hello everyone and welcome to another video on our own devices. I'm Jean Messier and today we're having a look at a fascinating piece of radiation detection equipment. This is a Fisher countoscope introduced by Fisher Research Laboratory Incorporated in the mid-1950s. Now, if you want to learn about the developmental history and operating principles of Geiger counters, please check out my previous video on the subject, link in the description. Today we will only be covering the specific design features and operation of this particular unit. So without further ado, let's dive right in. Fisher Research Laboratory Incorporated, not to be confused with the much larger Pittsburgh-based firm Fisher Scientific International Incorporated, was founded in Palo Alto, California by German-American electronics engineer Gerhard Fischer. Born in Landeshut, Silesia in 1899, Fischer studied electronics at the University of Dresden before emigrating to the United States, changing his last name to the more anglicized form without the C. In 1923, Fischer was contracted by the Federal Telegraph Company and Western Air Express, later Western Airlines, to develop radio direction finding or RDF systems for commercial passenger and airmail services. Fischer RDF systems, like the RF-45, soon became the gold standard for aerial navigation. However, pilots soon noticed that Fischer's instruments returned inaccurate readings when they flew over particular types of terrain. Fischer determined that these distortions were caused by large deposits of metallic ores in the ground, and, based on this insight, developed one of the world's first practical portable metal detectors. And he demonstrated this to none other than his friend Albert Einstein, who was very enthusiastic and predicted that soon handheld metal detectors would be in widespread use. Now, of course, Fischer was not the very first to develop a metal detector. That distinction likely belongs to father of the telephone, Alexander Graham Bell, who in 1881 built such a device to find the bullet lodged in the body of President James Garfield following his attempted assassination by Charles Guiteau on July 2nd. Unfortunately, the metal springs under Garfield's bed interfered with the signal, and the president died of infection 2 months later. And to learn more about that absolutely wild story, please check out the video I wrote about it over on Today I Found Out, link in the description. However, Gerhard Fischer was the first to create a commercially viable metal detector, which he patented in 1925. In 1931, he founded Fisher Research Laboratories on Emerson Street in Palo Alto to manufacture and sell his invention, which he dubbed the metalloscope. These proved extremely popular and successful, being used in all sorts of industries from geological prospecting to detecting saw fragments in lumber mills. As a result, Fisher Labs expanded rapidly, moving into a larger facility at 1961 University Avenue in 1939. Following the end of the Second World War, Fisher Labs began manufacturing radiation detectors for prospecting uranium, demand for which had exploded following the discovery of nuclear power. The company's first radiation survey meter, the Model C11 M-scope, was introduced in 1946. This featured a 5 by 9.5 by 9.5 inch or 13 by 55 by 55 centimeter wooden case weighing 5 pounds or 2.3 kilograms, and a thin-walled beta-gamma Geiger-Müller tube mounted at the end of a 36-inch or 90 centimeter walking stick to save the operator from having to bend over while searching for ore deposits. Readout was via speaker, headphones, flashing neon light, and a dial, with the only controls being an on-off switch and a volume control knob. Unusually, the readout dial was calibrated not in regular units such as milliroentgen per hour or counts per minute, but rather an arbitrary 0 to 100 scale of radiation intensity. Also unusual was the patent number printed on the case, which corresponded to Fischer's original metalloscope metal detector patent. This was later shortened to M-scope and applied to the totally unrelated series of radiation detectors for reasons, either brand recognition or pure laziness. I'll let you decide. Anyway, the next Fisher survey meters, the M-scope model C12, C15, and C18, were introduced in 1950. These were broadly similar to the C11, but used a high-voltage power supply with lighter batteries, making them better suited for field work. The dial on the C12 was calibrated in milliroentgen per hour with a switch for selecting between a 0 to 0.2 and 0 to 2 milliroentgen per hour detection range, while the C15 dial was still marked in arbitrary units. The C12 had an integral Geiger-Müller tube with a sliding metal shield for excluding beta particles, while the C15 was fitted with the same walking stick survey probe as the earlier C11. The C12 originally sold for $125 and the C15 $135, or around $1,700 and $1,800 today. Fisher also offered the budget C12A and C15A, which eliminated the speaker and only used headphones. Now, the third Fisher radiation detector introduced in 1950, the C18, was a radical departure from earlier models, measuring only 5 by 4 by 1.5 inches or 13 by 10 by 4 centimeters, weighing only 1.5 pounds or 680 grams, and featuring only a single earphone output. It was designed to fit in a coat pocket and was marketed towards amateur uranium prospectors. Appropriately, it retailed for only $35, around $470 today. In 1954 and 1955, Fisher introduced the model C16 and C16B, which sold for $120, around $1,440 today. Unfortunately, I haven't been able to find very much information on these models, though they appear to have been similar to the C12, only with a detachable rather than integrated GM probe. That same year, Fisher introduced the Model S Uranium Scout, a handheld metal case survey meter measuring 4.25 by 4.25 by 7 5/8 inches, or 11 by 11 by 19 centimeters, weighing 4.7 pounds or 2 kilograms, and retailing for $99.50, around $1,190 today. It also featured an internal speaker and headphone jack, but no neon flasher, a calibration dial, and a small radioactive check source fixed to the case by a short chain. A more sophisticated Model T, or Uranium Scout Deluxe, was also offered for $139.50, around $1,670 today. This had a separate detachable GM probe, which could be fitted with an optional walking stick or swapped out for a directional 2-tube gun-type probe. The sensitivity control knob had 1 times, 10 times, and 100 times settings, while the dial was calibrated for 500, 5,000, or 50,000 counts per minute, or 1, 10, or 100% uranium ore concentration. And this finally brings us to the countoscope, also introduced in 1955. In overall design, this is very similar to the Uranium Scout Deluxe, only it incorporates a 4-digit scaler to automatically count up the number of radioactive particles detected over a standard time interval, either 30 or 60 seconds. This is intended to help with conducting radioactive grid surveys, for example, when prospecting for uranium, or when conducting radiometric surveys of laboratories, power plants, and other workspaces. So let's actually have a closer look at this, and let me show you how it works. This unit comes in a very nice mahogany carrying case with a leather handle and a metal Fisher logo type on the side. Unsurprisingly, this originally retailed for a premium price of $465, around $5,600 in today's money. Opening this up, we have a green webbing shoulder strap, some advertising material, an instruction manual, and the unit itself. According to the sticker on the instruction manual, this was originally sold by Prairie Agencies at Units 39 to 42, 222 of Portage Avenue, which specialized in geophysical instruments and radios. And for all you Winnipeg history buffs out there, this site was originally occupied by the Enderton Building, which was built in 1910 and demolished in 1969 before being replaced by the current Royal Bank of Canada Tower. Right, so the countoscope couldn't be more 1950s if it tried, what with this lovely burnt orange crackle finish and the very retro lettering on the dial. This measures 10 by 5.5 by 5.5 inches, or 25 by 14 by 14 centimeters, and weighs a rather hefty 10.5 pounds or 4.8 kilograms, so that shoulder strap likely came in handy. This has a detachable GM probe with a bakelite cover. If we undo this screw and slide off the cover, we can reveal the unfortunately very crumpled Victoreen 1B85 detector tube. Now, as I mentioned in my previous video on Geiger counters, Geiger-Muller tubes are filled with a special mixture of low-pressure gases in order to function properly, and at the same time, the walls of the tube need to be as thin as possible in order to allow the maximum number of radioactive particles to penetrate into the interior. This, however, creates an engineering trade-off, since the thinner the wall, the more likely it is to collapse under atmospheric pressure. The first version of the 1B85 thus used a ribbed or corrugated wall to strengthen it, but in 1953, Victoreen introduced this smooth-walled version, which it claimed could withstand 3 times as much point or finger pressure. You can dent the tube wall as much as 1/4 of an inch and still obtain satisfactory operation. However, most still tended to collapse like this one after sufficient use. Thankfully, I was able to get my hands on an intact example and swap it in. The 1B85 is made of aluminum and uses a detection gas mixture of argon with an organic quench gas, probably ethanol. It can detect both gamma and beta radiation, but not alpha particles, since they cannot penetrate the aluminum walls. Now, later, Victoreen made a slightly modified version, the 6306, which used a bismuth cathode to increase sensitivity to gamma rays. Moving on to the top of the casing, we have a very swoopy, futuristic-looking carry handle, a jack for the probe cable, and 3 main controls. The knob on the left has 6 positions: off, sensitivity range 0 to 50, sensitivity range 0 to 150, and 3 battery check settings for the A1, A2, and B1 batteries, which we'll have a look at in a moment. Meanwhile, the knob on the right has 3 positions: off, and the 30 and 60-second time intervals for the staler. And finally, this is a calibration knob. To use this, you place the detection probe next to a check source, and then turn the knob until the readout on the dial corresponds to the standard activity of the source. Moving forward, we have a readout dial, aka the linear rate meter, which is not marked in milliroentgens per hour, but rather 2 generic relative intensity scales of 0 to 50 and 0 to 150, which roughly correspond to 0 to 0.1 and 0 to 0.3 milliroentgens per hour, respectively. We'll also notice the battery minimum marking on the scale. When the left-hand knob is set to the A1, A2, or B1 positions, if the needle does not climb beyond this mark, then that battery group needs to be replaced. Other than the scaler, there are no other output devices on this unit, neon flasher, speaker, or headphones, so unfortunately this cannot produce the iconic Geiger counter chattering noise. And finally, at the top we have our 4-digit scaler, which, as I mentioned previously, counts up the number of radioactive particles detected over a 30 or 60-second period. To use this, you set the right-hand knob to either 30 or 60, reset the scaler by throwing this little lever, then press the Count Start button on the right. The scaler will automatically stop counting when the selected time interval has elapsed. If desired, you can also push the meter mute button to shut off the readout dial. Right, so to open this up, we unlock these 2 latches at the ends, and the whole chassis lifts out of the housing. So, just like the homemade Geiger counter we looked at in my previous video, this takes a lot of different batteries. These 4 large metal brackets hold 2 pairs of 1.5 volt D-cell flashlight batteries, designated A1 and A2, while the smaller bracket holds a number 412 or U15 22.5 volt B battery, designated B2. Finally, this compartment at the bottom holds an F4BP 6 volt A battery, A2, and 2 number 467 67.5 volt B batteries, B1. Now, I was able to source all of these batteries except for the B1s, which are long out of production and very difficult to find. Thankfully, however, I was able to approximate them using 7 9-volt batteries chained together. Looking at the schematic included in the manual, very few of the major components are given numerical designations, so for the sake of clarity, let's assign some. GM1 is of course our 1B85 Geiger-Müller tube, and this is powered by a relaxation oscillator circuit comprising V3, a 6088 subminiature pentode, neon lamp NE1, 5785 diode V2, this capacitor, and this resistor. This circuit takes the 1.5 volts DC from battery A1 and steps it up to a 900 volt sawtooth waveform. This is then passed through V1, a CK1038 corona discharge voltage regulator tube, before being fed into the GM tube. When the GM tube detects a particle, the resulting pulse is sent to V4, another 6088 pentode, which amplifies it and sends it to V5, which on receiving each amplifier pulse sends power from 22.5 volt battery to relay R1, which increments the mechanical staler. Now, the average pulse rate is also displayed by the dial, aka the linear rate meter, which is a 0 to 50 microampere ammeter powered by the 135 volt B1 battery. Ordinarily, both sides of the ammeter are held at the same 135 volt potential. However, when a pulse from the GM tube activates relay R1 and the relay snaps back, a negative flyback current is generated. This current, which is integrated by this IN34 diode, this 50 microfarad capacitor, and this 100 kiloohm resistor, reduces the ammeter anode voltage and causes it to deflect in proportion to the number of pulses received per second. Pushing the meter mute button connects the B1 voltage to the negative side of the capacitor, bleeding off any stored charge and preventing the ammeter from deflecting. Finally, the 6088 pentodes V6 and V7, along with relay R2 and neon lamp NE2, form the timer circuit. When the count start button is pressed, one side of the 0.2 microfarad capacitor is connected to ground. This creates a pulse that is passed to the grid of V6, momentarily preventing it from conducting. The tube's anode voltage thus rises to that of the B2 battery, 135 volts, causing neon lamp NE2 to discharge. This then turns the grid of V7 positive and allows current to flow into and open relay R2. disconnecting B2 from this 100 kilo ohm resistor. Now, the only way to make V6 conduct is to turn its grid positive by charging the 0.2 microfarad capacitor. Selector knob S2 connects either one or two 100 mega ohm resistors in series with the capacitor, changing its time constant. The nominal time constant of this system would be 20 seconds for one resistor and double that, 40 seconds for two. But this time-adjust potentiometer allows this to be increased to 30 and 60 seconds respectively. Meanwhile, the opening of relay R2 routes voltage from B2 to V5, where it is used to operate relay R1 and the mechanical stator. Once the capacitor charges, V6 starts to conduct again, the voltage across NE2 is removed, V7 stops conducting, and relay R2 opens again, stopping the count cycle. And that, dear viewers, is the very clever operating principle of the Fisher countoscope, and a huge thanks to Mr. Julian Horn for helping me to figure out the innards of this device. Now, with all of the batteries installed and a new tube swapped in, this unit actually does operate, as you can see if I hold the probe up to this bag of uranium yellow cake. Unfortunately, however, despite my best efforts and those of my friends who work with vintage electronics, I was not able to get the mechanical stator to work. This is an old unit. There's a lot of parts in it that might have worn out or burnt out. I simply don't know. If I ever get it working properly, then I will definitely put out a follow-up video. Sorry about that. Anyway, getting back to the story of Fisher Research Laboratory, in 1955, the company also introduced a number of scintillation counters. And to learn more about that fascinating technology, please check out my previous video on the subject, link in the description. These were the scintillodyne that used a 1 by 1 inch sodium iodide detector crystal and sold for $249.50, around $3,000 today. And the more sophisticated scintilloscope, which used a 1 by 1.5 inch crystal, featured a special calibration scale for prospecting radioactive ores, came in a deluxe mahogany case like the countoscope, and sold for $487.50, or around $5,900 today. The gun-type probe could also be fitted for $555, or $6,600 today. In 1961, Fisher Labs moved from Palo Alto to a larger facility in Belmont, California, and 6 years later, Gerhard Fisher retired from the company, eventually dying in 1988 at the age of 89. In 1974, the company moved again to Los Bandos, California, where it remained until 2006 when it was acquired by First Texas Holdings Corporation and moved to El Paso. The Fisher brand survives to this day, best known for its Impulse line of portable metal detectors. And that, dear viewers, is a deep dive into Fisher Research Laboratories and the Fisher countoscope. You know me, I love me some radiation detection equipment, especially really neat mid-century modern pieces like this. This is a really cool discovery. Once again, a huge thank you to Julian Horn for helping me figure out the electronics in here. Thank you to all of you for watching. I will see you next time in another video where we'll look at yet more fascinating radiation detection equipment and other devices just like this. Until then, I'm Jean Messier from Our Own Devices. Have a great day.